In the last video in this series, number 13, we discussed some of the physics around the Schwarzschild metric for a non-rotating, uncharged black hole. And that rather lengthy discussion included how measurements of the velocity of objects, or the velocity of a beam of light, would be affected by the metric. In particular, we looked at objects or light travelling directly towards the black hole, and also light in orbit around the black hole. In this video, number 14, we will look a little more at the curvature of time and space around a black hole and discuss a couple of other frames of reference other than the outside rest frame, and these will include what we will call the freely floating frame and the shell frame. The Schwarzschild metric tensor for our four-dimensional spacetime was shown, or rather stated with some justification, to be this, where capital G is the universal gravitational constant, capital M the mass of the black hole, c the speed of light, and little r the distance away from the black hole. This metric tensor varies with position, and the only changes in position that we're thinking about are in the radial direction r. We also define the Schwarzschild radius rs as 2gm over c squared, so that by substitution of this, the Schwarzschild metric could also be written like this, or even like this. And we discussed the fact that this metric was based on the use of spherical polar coordinates, and that only the radial and time dimensions have actually been curved by this non-rotating, uncharged black hole. This means that as there is spherical symmetry to this whole situation, and that these last two entries do not reflect any curvature of the actual space, then we can work with this much simpler two-dimensional metric tensor, with or without the rs replacing the 2gm over c squared. Let's now use this two-dimensional space-time metric to consider some more basic ideas around black holes, and we'll first look a little more closely at the spatial curvature around a black hole. This Schwarzschild metric for the two dimensions r and t means that the square of the space-time interval between two events can be written as this. Well, we've gone back to showing the measurements made in the RT system in red. We can, of course, use this version of the space-time interval for two dimensions if we include the Schwarzschild radius rs instead of 2gm over c squared. Or we could even use this if we rearrange the two brackets. And you may notice here, and in what follows, we have left the Schwarzschild radius rs in black, even though it has been measured using the red RT system. Now, in order to look at the spatial curvature around a black hole, we'll concentrate on this last version of the space-time interval formula, and let's suppose that we had two events that were measured to take place at the same time by the outside red observer. That would mean that dt, their measurement of the time difference between the two events, would be 0. The expression for the space-time interval squared reduces to something which describes not so much the space-time interval, but the space interval. It describes the distance ds between two events that happen at the same time, as measured by the outside observer. Taking the square root of this expression gives us ds. So, having fixed the time in the red frame, dt equals 0, this equation could be said to describe the measurement of a small distance in some small region outside of the Schwarzschild radius, where both ends of that distance, if I can use that phrase, are measured at the same time. We could be talking about two events a small distance apart which happen at exactly the same time as measured by the red frame of reference. In this region outside the event horizon, the value of r is bigger than rs, and so this bracket is greater than 1. This means, of course, that as dr is positive, then the distance ds must also be positive and therefore space-like. Now, we could represent this on our usual space-time diagram, but on account of the fact that time is constant, we could equally well draw a two-dimensional space diagram as long as we think in terms of measurements being made only along one radius and we don't imagine changing the angle around the black hole in any way. Here's the situation in two-dimensional space, with the event horizon round the black hole of the mass m shown as a green circle. The small distance dr is shown in the region of the radius r and is shown fairly large for clarity, although in reality dr is meant to be infinitesimally small. The two events are shown as two yellow dots. Now let me stress this is a two-dimensional space diagram, and the formula we'll be looking at will be for one particular red time t measured by the outside observer. In other words, dt equals 0. The radius r could, I suppose, be thought of as being in any outward radial direction, and we could even show the theta on this space diagram, but we know that there is angular symmetry, and so we're only interested in thinking about the radius measured horizontally in this diagram to the right, measured from the central mass capital M. The situation is that we are dealing with two events at different places but happening at the same time as measured by the outside red observer. So let's imagine that event number 1 happens at the yellow dot at distance r from the central mass, and event number 2 happens at distance dr further away. The events could, for example, be the presence of two ends of a measuring rod, one at each of these yellow dots. At that specific time, the distance dr would then be the distance between the 2 points as measured by the outside red observer, essentially the length of the measuring rod as far as that outside observer was concerned. However, the actual distance, the proper distance between the 2 points, is given by ds, which according to the Schwarzschild metric, which has dt equals 0, is given by this formula. This ds, the proper distance, is clearly different from the dr that the outside observer measures, and it's all because of the curvature of the space-time due to the presence of the black hole. In this case, as we are assuming that the points are outside of the event horizon, then we can say that little r is bigger than rs, and that means that this whole bracket is greater than 1, giving us the result that the proper distance between the 2 points ds is greater than dr, the distance measured by someone using the outside red frame. You could put it the other way, I suppose, and say that the measured value dr is too small on account of the fact that the region of space under consideration is near the large mass m, and so the space is distorted or curved. If you like, there is a form of length contraction as far as the red observer is concerned, and this has nothing to do with special relativity or moving frames of reference. It is a gravitational length contraction, and has more to do with the stretching of the basis vectors of the frame of reference due to the curvature of the space-time by the black hole. Someone using those proper coordinates in this region, the curved or stretched coordinates which the Schwarzschild metric embodies, would measure that proper distance, ds. If you recall from earlier videos on Riemannian geometry, we had this kind of equation for a vector v in two-dimensional space. V equals v1 e1 plus v2 e2. And if we take just one spatial dimension like we have here for the r direction, we could simply write v equals v1 e1. Then, in simple terms, you can see that the actual size of the vector v will depend on both the contravariant component of that vector, that is, its measured value v1, multiplied by the basis vector. If the basis vector stretches and goes bigger, then because the vector itself hasn't changed, it must mean that the measured value v1 is smaller than it ought to be, and of course vice versa. The space around this large mass capital M has been stretched or curved by that mass, and so a different metric has had to be used to measure that space, the Schwarzschild metric. However, we are using the old coordinate system, the red system, which our Schwarzschild metric is a function of, and so our measurements in that red system will not be correct. The conclusion of all this is that anywhere outside the event horizon of a large mass, an outside observer will measure distances to be smaller than their proper distance, and this is due to the curvature of the space in that region, caused by the presence of the large mass m. The equation that we've just been considering shows this clearly. and it's all in the mathematics. However, sometimes we like to use pictures to help visualize what's going on, and in some of the earlier videos in this series, when we were considering two-dimensional curved spaces, we started by looking at the space head-on, like this. But then, because we knew that it was really curved or stretched in places, we imagined tilting the space, and we could visualize the curvature by picturing it embedded in an imaginary extra dimension, something like this. In this earlier diagram, after tilting, this perspective view shows the two-dimensional space lying horizontally, but with an extra imaginary dimension in the vertical direction. In this case, it is shown curving upwards, but it equally well could have been shown curving downwards. In very simple terms, this kind of picture helped us to realize that the grid lines of the measuring system, which looked so innocent in the first diagram, were actually somehow representing, or rather measuring, stretched space with different proper distances. The basis vectors, E1 and E2 in that case, were greater than 1 in the bulged region, and perhaps not even orthogonal to one another in some places. The metric tensor had to have this curvature because the space itself wasn't flat. There was no way in which that metric tensor could be made into that of Cartesian coordinates by some transformation or other. That was all for two-dimensional space alone. Now let's try and show some kind of picture like that for our two-dimensional space diagram for the black hole and this gravitational length contraction. In order to help to see it, we'll put the artificial boundaries on this two-dimensional space. Remember, this isn't space-time, as we're keeping time constant for the moment. And we'll shade it in slightly like we did for spaces in earlier videos. And then, in order to imagine the extra dimension, we'll imagine tilting the space to get some perspective into a hypothetical extra dimension. You have to imagine that this surface is now horizontal. However, we can now add the imaginary extra dimension which will show the curving of the space around the black hole, and this time we'll do it in the downward direction of the screen. And you'll notice that we have stopped at the event horizon of the black hole, the green circle. For this two-dimensional representation of the black hole, this whole thing is meant to look like the surface of a kind of upside-down protrusion. The top flat surface that you see here should not really be visible. Because of the way we tilted the surface, we should really be seeing the inside of the protruding surface, which is the surface of the distorted space, a bit like this. However, the inclusion of the top flat surface in the diagram does help to see the measured values of R before we got the insight from this extra imaginary dimension that we added, so we'll leave it in the diagram and we'll use this representation. At large values of R, far away from the mass m, it should be obvious from this picture, just as it was from the mathematics, that the surface is flat. However, as you get nearer and nearer to the black hole, the distortion gets worse. The small distance dr between the 2 points measured at the same time using the red coordinate system can be illustrated more clearly by this red line between the 2 yellow dots. However, the mathematics is telling us that this is smaller than the actual distance, the proper distance, ds, between the 2 points. And we can actually see this, or rather better appreciate it, by looking at what the curved surface would suggest that this distance really is, the proper distance. The red line dr here maps onto a much bigger distance, ds, on the curved surface, shown here in blue. And this picture illustrates exactly what we had in our formula for ds at a given time. ds is bigger than dr. You should also appreciate, of course, that this effect would get more dramatic nearer to the event horizon. Here we have the same distance measurement dr being measured closer to the black hole, and we find that the value of ds, the proper distance, is even larger, and that too, of course, also agrees with what we would get from the formula. Perhaps another way to illustrate this would be to imagine a small rod of proper length ds at different places. This proper length could be measured by someone near to the rod, and it's shown here in blue and at a large distance away from the black hole. Clearly that person way out here will measure the length of the rod as ds, whereas the outside red observer, using their set of coordinates, would measure it as dr. However, in this flat region of space-time out here, assuming no massive velocities between these observers, dr would be measured to be exactly the same as ds. There's no gravitational length contraction out here. On the other hand, as the rod and blue observer slowly approach the event horizon of the black hole, the space-time becomes distorted, and so here, even though the blue observer sees or measures no change in the length of the rod, the outside red observer measures its length dr to be smaller. And this difference gets more exaggerated nearer to the event horizon, and it will tend towards dr being measured to be 0 at the event horizon, despite the fact that the observer alongside the rod measures the proper length ds still to be unchanged. And if you think about it, all of this goes towards explaining, or rather helping to clarify, how the black hole distorts or curves the space-time around it, and how measurements made by an outside observer who has to use curvilinear coordinates are too small. But what about time? Can we now think in terms of how the time around a black hole is also curved and distorted by the presence of this mass, capital M? So let's look at what might be called temporal curvature. Once again, given the spherical symmetry of a black hole, we can start this discussion about the curvature of time with the two-dimensional Schwarzschild metric for r and t, and ignore the angles theta and phi. We could use this, or this, or this. However, we will probably concentrate on this last version of the space-time interval formula for the Schwarzschild metric, as it perhaps is a little easier to appreciate the importance of the Schwarzschild radius, rs. For this discussion, we will start by considering a single place in this space-time, a place where something happens at two different times. It could be that two flashes of light occur from the same point in space, but they're separated by a time dt. In that case, of course, we would assume that r is constant, same place, and so dr in this case must be set to 0. This then would give us, for the square of the space-time interval ds squared, this formula. Now, given once again that we are considering a place outside the event horizon, it means that we can take little r to be greater than rs. And so once more, this bracket must be taken to be positive, making ds squared negative in this case. This space-time interval is actually time-like. It's really a measurement of the time difference squared. However, we know that we can always redesignate ds squared as minus d tau squared, and so we can write this time-like ds squared as a positive quantity, d tau squared, like this. If we then take the square root of all this, we can say that the proper time, d tau, and the measured time, dt, are related by this formula. Now remember, we're considering a single place in space-time at a position r. So let's now imagine that two events happen at that place, but do so at different times. We'll take the separation of those times to be dt as measured in the red frame of reference. Instead of flashes of light or whatever, the situation could be that we have a clock at the yellow dot at position r, and that two ticks of the clock are separated by some time period. If you like, the events are the tick of the clock at different times, but at the same place. Taking this equation then, and assuming as before that little r is greater than rs, we're outside the event horizon, we can see that in this case, the multiplying bracket is less than 1, even when square rooted, and so d tau is less than c dt. And of course, taking the speed of light to be 1, This means that the proper time difference d tau is less than the time dt measured by the outside observer. This would mean that if someone at position R, who's obviously situated in the gravitational field of the black hole, were to send out a flash of light at each of these ticks of their clock, then although they would measure them separated by a time d tau, some distant observer in the red frame who is outside of that gravitational field would measure a longer time dt between the ticks. There's a kind of gravitational time dilation or slowing down of the clock. The outsider measures times between ticks to be longer, and once again this has nothing to do with special relativity and moving frames of reference. It is a gravitational time dilation. Also, if instead of the ticks of a clock we could think in terms of the oscillation of a light wave as a form of ticking, this would mean that if a beam of light of a particular frequency were to be sent out by someone at R within the gravitational field, and that beam of light were to be received by a distant observer who was outside of the gravitational field, then that outside observer will measure a longer time between each oscillation of the light wave. The time period will be increased as far as the outside observer is concerned, and therefore the frequency of the measured light will be reduced. The speed of light being constant for everyone would mean that this lower received frequency would result in a longer wavelength being measured by the outside observer, shifting the colour of the light towards the red end of the spectrum. This is the gravitational redshift. For example, any light received on Earth, which itself has a fairly weak gravitational field, from a distant object which is within a high gravitational field, will be redshifted when it is received on Earth. This would be on top of any Doppler redshifting that might take place due to the relative motion between the distant object and the observer on Earth. It should also be obvious, I suppose, that light received by someone in a high gravitational field from a source of light in a lower gravitational field will be blue shifted. All of these effects that we've looked at so far relate to the outside observer's measurements or impression of the situation close to the black hole. But it's worth mentioning again that even though the outside observer measures all these strange effects, the person who is freely falling into a black hole would feel nothing, unless or until the effects of tidal forces come into play. And with any such freely falling object, the space would appear to them to be locally flat, just as though they were freely floating in outer space far away from any gravitating masses. Assuming that the tidal forces were not large enough to be noticeable, anyone falling into a black hole in an unpowered spaceship would simply be floating in that spaceship, unaware even of the presence of the black hole. They could therefore even use a simple Minkowski metric to make measurements in that local region, and so for them, in their freely falling spaceship, they would have this metric tensor for two-dimensional space-time, -1, 0, 0, and 1, so that ds squared was minus dt squared plus dr squared, where the blue r and t refer to measurements made in the freely falling spaceship, as opposed to those by the outside observer. If we wanted to consider all 4 dimensions of space-time for this free fall, then all the spherical polar spatial coordinates would of course come into play, and this could be used as the local metric for that flat space-time. Again, as mentioned earlier, this sense of the flatness might even be a good approximation while crossing the event horizon, depending on the mass of the black hole. Also, and this might sound a bit strange, for a very, very large mass black hole, the tidal forces would not really become noticeable until well inside the Schwarzschild radius, and so the space-time near the event horizon would seem flat and without any noticeable tidal forces. For example, the black hole assumed to be at the centre of our Milky Way is believed to be of the order of 4 million times the mass of the Sun, and this would give a Schwarzschild radius of about 10 to the 10 meters. At that distance from the centre of the black hole, on or near its event horizon, the gravitational field lines would still be reasonably close to being parallel, and although the value of the field would be rather large, the stretching effect on normal-sized objects in a spaceship would still probably not be noticeable. On the other hand, if the mass of the black hole were much, much smaller, then its Schwarzschild radius would also be much smaller, and the situation would look a bit more like this. Here, you can see that although the mass is smaller, the event horizon is much closer to the singularity, so that near to this event horizon, the tidal forces will be much greater. The freely falling observer would notice the stretching and the squeezing from those tidal forces, probably even before they reached the event horizon in that case. Okay, that was for someone freely falling into a black hole. Now let's use this one-dimensional space or two-dimensional space-time with the Schwarzschild metric and the outside observer measuring red r and red t. But this time, think about someone who is maintaining a constant position r away from the black hole. We'll call this the shell frame. They may be in a spaceship trying to accelerate away from the black hole, as illustrated here in this two-dimensional space diagram. Again, there's no time dimension included here. Or they may be standing on some sort of hard, thin shell of radius r, which is somehow surrounding the black hole like this. Now, don't ask me how the shell will be kept in place, because what I want to stress is that in both these situations, general relativity tells us that the person is accelerating. Let me remind you, in Newtonian gravity, things are modelled in such a way that somebody in free fall towards a black hole is considered to be accelerating due to the force of gravity on them. If they are then stopped by the shell, or their spaceship switches on its engine so that the spaceship maintains a distance r from the black hole, they are considered to then be at rest. Newtonian mechanics would say that the force of gravity on them to the left from the black hole is balanced by the force on them to the right from the shell or the floor of the hovering spaceship. Contrast that with how we now think about such things in general relativity, where we don't think in terms of any force due to gravity. When in free fall, the object is in an inertial frame. Yes, it may be travelling at some velocity relative to another observer, but as far as they are concerned, observers in the spaceship which is falling are at rest. On the other hand, when they are on the shell or in a stationary hovering spaceship, they are considered, by general relativity, to be accelerating. So let's now consider the frame of reference of someone who is somehow maintaining this constant position r away from the black hole. Whichever way we describe this particular frame of reference, it will have to cope with the presence of what seems like a gravitational force on it. I say seems because all that is happening is that there is a force acting on the person's feet, either from the shell or from the spaceship floor. This is clearly not, therefore, a freely floating frame. However, the form of the metric for such a frame of reference can be made to look approximately flat if we add what we might call a force of gravity. In doing so, we would be interpreting the force from the shell or from the floor of the spaceship on their feet to be a normal reaction in response to some gravitational force or other in the opposite direction. It's a bit like standing on the Earth. The sense in which we feel what we call the force of gravity is really because we feel the force upwards on our feet. Being on the surface of the Earth can actually be considered to be in a kind of flat space-time as long as we include the force of gravity as an extra idea. And the same will be true for someone on the shell or in the hovering spaceship. The fact that r is constant means that we could assume that someone on the shell or hovering is in a kind of flat space-time. Let me explore that in a bit more detail, and in doing so I will use the phrase on the shell to mean either on the shell or hovering in the spaceship, both the same. Granted, the form of the metric for such a person is still the Schwarzschild metric, which, considering only r and t and ignoring angles, is given by this, and will give us this space-time interval equation, as we wrote down earlier. However, the fact that on the shell the value of little r is constant means that, although different to one another, these two brackets are each separately constant. In other words, these are fixed, provided we are on the shell. If that's the case, then, for this situation, we could consider redefining our time and space measurements. And we could redefine them in such a way that this whole thing effectively became a new c squared dt squared for the shell, and this became a new dr squared for the shell. That would be easy enough to do, to redefine the red r and t into something else. We could give the new time and distance measurements new letters, say blue t tilde and blue r tilde, in which case the conversion equations could be these. Don't forget, these brackets are constant on the shell. Given this coordinate transformation, that would give the space-time interval on the shell, and in these coordinates, as ds squared equals minus c squared dt tilde squared plus dr tilde squared. And this, of course, looks a bit like the Minkowski spacetime, with the metric tensor being like this, minus 1, 0, 0, 1, for these new coordinates. In other words, when on the shell or hovering, things can be measured using these coordinates, and for all intents and purposes, the sense will be that the spacetime is flat, because these Cartesian-type coordinates, which arise from this Minkowski metric, can be used to measure it. However, you may realize that there is a sense in which this is not, strictly speaking, flat spacetime. What do I mean? Well, to get this to be the case, we had to transform the red t by the square root of this factor to get the blue t tilde, and the red r by the square root of this factor to get the blue r tilde, and both of these are functions of the position r. These factors are not constant at varying distances from the shell, or what we might call varying heights above the shell. Perhaps we should say that the space-time in this region near the black hole is locally flat. In a very much less dramatic sense, you could say that this is similar to our situation on Earth. We have a much weaker gravitational field, of course, but given that we are on Earth, or more or less a fixed distance from the centre of the Earth, means that we can consider space-time essentially to be flat for us. What we add to that, of course, is the fact that the Earth, like the shell or the hovering spaceship, prevents our free fall towards the gravitating mass m by applying a force to us against our natural geodetic falling motion. And it is this force on us, on our feet, that we sense as a force of gravity pushing us down towards the gravitating mass of the Earth. Now, we're not finished with black holes just yet. As we hinted at in an earlier video, we want to think about a different set of coordinates that can be used to make measurements in the vicinity of a black hole, and also within its event horizon, inside the event horizon. These coordinates, sometimes called crustal coordinates, will be extremely useful in helping to explain, or rather appreciate, some of the phenomena around a black hole, without having to work through all of the mathematics. And we'll begin to explore these crustal coordinates in the next video, number 15. This video number 14 has discussed various scenarios around a Schwarzschild black hole. In the next video, we'll have a discussion of crustal coordinates and the usefulness of those coordinates in which the velocity of light is not measured to change near a black hole.